All right. Good afternoon, everyone. I am Pavlos Protopappas. I am the Scientific Program Director for the Institute for Applied Computational Science, and I will be here to introduce the speaker. We have one more talk this semester, which is happening in November 30th. Julia Ling for Citrin will be giving a talk about machine learning for materials. That's November 30th, I guess in the same room. Huh? So it is my pleasure to introduce Flavio. Flavio is a colleague, friend, one of us here. Flavio Calmon, I said it right?
Yep.
Flavio did he started his career in Brazil. That's where she's from. And then he did a master's in Campinas, which I just found out is outside Sao Paulo. Welcome, by the way. And then a Ph.D. at MIT, a year of postdoc at IBM, and now he's an assistant professor here at CIS. His research interest, at least one thing I know is about fairness, and that's what he's talking about today. His title is Representation, Fairness, and Privacy. There was some bottleneck when I read it.
Yeah, I removed it, and we will talk about the bottleneck.
So we got rid of the bottleneck, and we're ready to go. Please help me to welcome Flavio.
Hey. Thank you so much. Well, thank you so much for inviting me. I'm excited to be here today to talk about some of our results done here at Harvard by my group on representations, fairness, and privacy information-theoretic tools for machine learning. So the results that I'm going to talk about today were done by an amazing group of students. Lisa, who is an undergraduate in computer science here at Harvard, Sean and Hao, who are PhD students here at CIS, Burke, who's a postdoc, and Salman Salamachin, who's a PhD student at MIT. So I'm going to start my talk with a quote that I heard a lot a couple of years back when I was working at IBM as a data scientist, which is a quote from the CEO of the company, Ginny Rometty, where she states, "I want you to think about data as the next natural resource." And if you think about other natural resources, things like oil, natural gas, uranium, and so on, what you realize is that much like these other natural resources, data is harvested and used to provide useful services, useful public utility. But at the same time, just like these data resources, like these natural resources, data must be handled with care. So on the one hand, with the massive deployment of systems that collect data, that learn from data, that process data, we get all these useful services, things like search, social networking, online advertising, online shopping, and so on. But with big data also comes big responsibility. And we want to make sure that these systems do not overstep. Specifically, we want to make sure that these systems, the systems that work with our data, ensure privacy. Right? We want to make sure that these systems are fair, that their performance does not vary condition on the race or the gender of the user that's producing the data. And we also want these systems to be transparent. We want to be able to, up to some degree, even though they might be complicated, based on complicated machine learning models, we want to be able to understand and interpret the decisions made by this system. And today's talk, I'm going to share with you some information-theoretic results that can enable us to understand these different aspects of systems that learn and process data. And the results that I'm going to present today come from my deep-seated belief that theory matters, and then theory can help us understand fundamental aspects of these challenging data problems. Okay? And specifically, I'm going to be using one kind of theory, information theory, to understand fundamental properties of some aspects of privacy, fairness, and transparency. Okay, so today's goal, this talk has a bit more theory, so bear with me, but I'm sure that everyone here in this room can understand at least the gist of the theoretical results that I'm going to present here today. And I'm going to introduce information-theoretic tools that are useful in fairness, privacy, and also in a broader application area, the area of representation learning. And specifically, we're going to be focusing on one tool, one theoretical tool that will be the workhorse of what we're going to do today, called the principal inertia components. Okay, so hopefully by the end of the talk, you have some intuition of what this theoretical tool means and how it can be applied to these different problems. Okay, so before I go on and jump right into the theory, I just want to give you a bit of more motivation first. So this is the outline of the talk. I'm going to start with some motivation of the problem that we're looking at, the problem of fairness, privacy, and representation learning, and give examples of the specific, very limited settings that we're going to be looking at today. Then I'm going to talk about the main theoretical workhorse that we're going to be using, the principal inertia components, then move on to applications on fairness, privacy, and representation learning. And if I have time, I'll conclude with some of the exciting ongoing work that my group is doing here at Harvard. Okay, so going to start with a bit more motivation of the problems that we're going to be looking at today. So machine learning algorithms are increasingly used in applications of individual level consequence. Applications such as recidivism prediction, predicting if someone at the moment they're charged with a crime, if they're going to commit a crime again. Personal finance, things like automated loan approval, credit scoring, and so on. And employment and hiring decisions, things like what ZipRecruiter does, where they match job seekers with job hires. A natural question to ask in these systems is, do the algorithms that underlie these systems discriminate on race, gender, or some other legally protected attribute? Okay, so why do we care about this problem? Well, we should care about this problem hopefully because everyone here wants to live in a fair and equitable society, but you should care about this problem because it's also the law. Right, so if you finish your degree here at Harvard and you go on to, I don't know, do your startup where you're using machine learning to match job seekers and job hirers, there are clear regulations from the United States government of what constitutes discrimination, and you want to make sure that your company follows the law when you're deploying machine learning systems. And by the way, just to make this crystal clear, whenever I mean discrimination in this talk, it's not its usual statistical sense of discrimination. I mean discrimination in the social science sense as the prejudicial treatment of an individual based on membership in a protected group. And unfortunately, machine learning algorithms can discriminate. An example that you can do right now on your phone is that you can go to Google Translate and type in she is a doctor, he is a nurse, translate it to Turkish. Turkish is a gender-neutral language. It doesn't have gender pronouns. Get that translation and translate it back to English. The pronouns will be flipped. You're going to have he is a doctor, she is a nurse. Why does this happen? Well, hopefully it doesn't happen because the software engineer that implemented this algorithm is sexist. Most likely what happened here is because the translation system is based on some machine learning algorithm that learns from data, picks up on these biases that exist in the data, and tends to propagate it automatically. And this automated bias propagation is particularly concerning in applications such as recidivism prediction. Right? So today in some states in the United States, if you're charged with a crime, you're going to be taken to a police station, and someone in that police station is going to fill out a questionnaire about you, feed it to an algorithm, and that algorithm will give you a score, which is your chance of recidivizing, of committing a crime again or not. And that score may or may not be used by a judge to set your bail. And this is just one example of a much debated report by ProPublica that indicates that there might be a variation of performance in some of these algorithms conditioned on your on average on the race of the data that's been input into the algorithm. And there are many other examples of discrimination by machine learning algorithms and for example, facial recognition and so on. So why do we observe discriminatory behavior in these algorithms? Right, so we're going to be looking at there are many sources of discrimination. We're going to be looking at two specific sources. Okay, one potential source is what is called disparate treatment. And this happens when you have a machine learning model and you have your decision variable X that you're used to make decisions in this model. For example, in the criminal recidivism prediction case, there might be age and criminal history. And you also use as an input to the model some sensitive attribute S, for example, your race. In this case, you have what can be defined as disparate treatment because you're using your sensitive attribute directly in the decision making of your model. More pervasive nowadays is what is known as disparate impact. Okay, when your sensitive attribute is not used directly as an input, but there are other correlated features in the input of the model, other features in X that are correlated with S that might serve as proxies for discrimination. Just being a bit more precise on this specific angle of disparate impact, one way you can think about this is in terms of probability distributions. Okay, so if you look at the distribution of the input features of your model, condition on the sensitive attribute S, let's assume just for the sake of example that S is binary, 0 or 1. So condition on S, the distribution of your input features may change, leading to different output distributions in your model, and it may also lead to the different performance of your model on average across these two different populations. So when we talk about fairness in this talk, what we're going to be looking at is our goal in fairness is to systematically identify proxies for discrimination. So this is what we're going to do today here in the context of fairness. We're going to try to identify potential outcomes of X that are highly correlated with the sensitive attribute S and might also be used as important decision variables by your model and thus serve as proxies for discrimination. So whenever I talk about fairness today, our goal will be to systematically identify outcomes of X that might serve as proxies for discrimination. So that's the first problem we're going to be looking at. The second problem that we're going to be looking at using the same set of theoretical tools is a problem in privacy. It's what I'll call here the privacy utility trade-off. And we're going to be looking at this at one specific setting, which we call the one-shot release model. I'll define this more formally a little bit later in the talk, but I'm going to motivate it first with an example. So assume that you have a user, and this user has some information that they want to keep private. For example, that information might be if they're a Republican or a Democrat. Okay, it's their political preference. And at the same time, this user wants to disclose some data to a data collector. And why is the user revealing the data? Well, in order to receive some service from this data collector. In this example, the data might be your TV show ratings. And the recommendation, and the service is a recommendation of a new TV show to watch. Right? If the user releases the data as is, he's going to receive, or the user is going to receive the best recommendation possible based on the data. But at the same time, the data collector may be able to infer the private information from the user. In this case, the user likes the Colbert Show, doesn't like Fox and Friends, likes the Daily Show, chances are, might be a Democrat. What can the user do about this? Okay, the user can distort the data. They can change the data before they disclose it. And the user may change it in the form of erasures, for example. They may erase some movie ratings and choose not to disclose them. In this case, privacy may be assured. You know, everyone likes Lost, everyone loves Friends, everyone really loves Game of Thrones, independent if you're a Republican or a Democrat. But specifically, the quality of the utility of the recommendation that the user receives might be worse. Specifically, they might receive a recommendation for a show that is very popular, but they might not be specifically interested in. And today, in this talk, what I'm going to present is a set of information-theoretic tools that can help us understand the fundamental trade-off between privacy and utility in this one-shot disclosure setting, closure setting. Okay, and just to make this clear, this privacy utility trade-off model, I'm sure many of you here heard about differential privacy. Differential privacy is a very popular and very strong notion of privacy. The angle that I'm coming at this problem is slightly different. It comes from the Information Theory Society. There's been a growing body of work that studies the intersection of information theory and privacy, particularly over the past few years. And it's within this literature that the results that I'm going to talk about today is inscribed. Okay, so that's the second problem we're going to be looking at, privacy. We're going to be looking at it using the same set of theoretical tools. The third problem is the problem of representation learning. And we're going to show how the principal inertial components, these theoretical tools that I'm introducing today, can also be used to reason about representations learned by complicated machine learning models. What that means is that if you have a data, a random variable X, that might be a piece of text, that might be images, that might be apples and oranges, I don't care. Like in many machine learning algorithms, the first step that you're going to do is to learn a real representation of this data, representation that maps your data into a real vector that you use for training. And specifically, we're going to be looking at maximally correlated representations and how to produce representations for two pieces of data, for example, a text and an image, or we're going to look at one example, which is cuisine and ingredients, and understand how to produce maximally correlated representations. And that will allow us to scale up one traditional statistical method called correspondence analysis. So in short, this is what we're going to be doing in the next 40 minutes of the talk. In fairness, we're going to be studying how to systematically identify potential proxies for discrimination. In the privacy context, we're going to be characterizing the best privacy utility trade-off from one specific perspective, an estimation-theoretic perspective. And in representation learning, we're going to be introducing tools that will help us reason about representations learned by complicated machine learning models. And the workhorse that we're going to use for these three applications is a set of information-theoretic tools that I call the principal inertial components. And that's what I'm going to introduce next. Okay? So for the second part of my talk, let's all put our math or theory hats on. And we're going to be talking about the many facets of this information-theoretic creature called the principal inertial components. And you can think about the principal inertial components as providing a fine-grained decomposition of the dependence between two random variables. Okay, so bear with me while we go through this. And what I'm going to do next is that I'm going to present 3 equivalent definitions of these guys, of the principal inertial components. Each definition will be useful for each of the applications that I motivated in the previous part. Okay? So first definition of principal inertial component emerges in the context of maximizing correlation. So assume that we have 2 random variables, x and y. For example, x might be an image and y might be a caption, or something like that. Right? And our goal is to find 2 functions, one function of x, one function of y. For example, I'm going to compute one function of x, f of x. You're going to compute one function of y, g of y. These are real functions, so even though x and y might not be even distributed, might not even be numbers, we're going to map them into a real number. And we want to find a representation, this f of x and g of y, that is maximally correlated. Okay, that maximizes this correlation here. And to avoid trivial results, we're going to restrict these functions to have 0 mean and unit variance. If we were to solve this function, this optimization, if we were to find these functions that maximize correlation, the solution to this optimization problem is something called maximal correlation. The study of maximal correlation, the earliest that I know of, is from Hirschfeld in 35. Raynier and other mathematicians studied it. And we call the maximal correlation the square root of the largest principal inertial components. So let's assume that we managed to solve this optimization problem. And let's call the solution of this optimization problem f1 and g1. So we're going to play the same game again. I'm going to find a function of x. You're going to find a function of y that's maximally correlated. But now we're going to impose the additional restriction that these functions are orthogonal, uncorrelated with the previous functions that we found. And if we are able to solve this problem again, the solution to this optimization problem is the second largest principal inertial components. If we solve it, let's call the solution to this optimization f2 and g2. Solve it again, we get the third largest principal inertial component, and so on. So the sequence of correlations that we find are called the PICs. And the sequence of functions, they're orthogonal functions. They form a basis for the space of finite variance functions of x and y. And we call this sequence f1, f2, g1, g2 the principal functions of the joint distribution of x and y. And this will be very useful in representation learning. Okay? So that's the first definition of the PICs. The second definition, which is entirely equivalent to the first one, comes from mean squared error estimation. So consider the following estimation 101 problem. Okay, so we have a hidden variable x, and what we observe is a correlated random variable y. And our goal is to estimate x from y. Okay, so if we were to solve this problem, one objective that you could have is called the mean squared error. Right? We could try to find this value of x hat that minimizes the mean squared error, the squared loss, of reconstructing x given an observation of y. And the estimator that achieves this is the conditional expectation operator. And this value is what we call the MMSE. Of course, x might be a piece of text. You know, x might be an image, right? X might not necessarily be a real number. So we're going to slightly generalize this question and ask, what is the function of x, the real function of x, that we can estimate with a minimum mean squared error? Okay, so if you were to solve this problem, the smallest MMSE that you get is 1 minus the largest principal inertial component. And when you restrict the function to have 0 mean and unit variance, and the function that you can reconstruct with the smallest MSE corresponds to the first principal function that we saw in the previous slide. If we solve this optimization problem and continue to add in orthogonal constraints, let's say we found a function that's the easiest one to estimate that has 0 mean and unit variance. Now we want to find the second function that's uncorrelated to the first one. We get the second principal inertial component, and so forth variationally. And if you look at this and you squint, you can already see that probably this definition is useful in privacy, right? Because in privacy, there's something that we want to hide about x, about our data. And we want to make sure that any function of that data cannot be reliably inferred from some information that I disclose, right? So we're going to be using this notion of the principal inertial components as a decomposition of MMSE in the context of privacy. And the third definition is a little bit more technical, which is the question of what is the spectrum of the conditional expectation operator. So the space of all finite variance functions of a random variable y is a vector space. And we can think about a conditional expectation operator that maps the space of all finite variance functions of y to the space of all finite variance functions of x, given by this conditional expectation. For the math experts in the room, this is just a linear operator. Like any linear operator, you can talk about singular values and singular vectors of this operator. And the singular values, the squared of the singular values of the conditional expectation operator is the principal inertial components. And this will be particularly useful in fairness. And the reason the PICs give you a fine-grained decomposition of the dependence between two random variables is because when your random variables are discrete, you can write the joint distribution, you can decompose it in this way. So the joint distribution between x and y is the product of the marginals. You know, if x and y were perfectly independent, this would be the distribution, right? And the PICs give you this coupling. You know, it gives you the decomposition of the dependence between these two random variables. So if you had independence, you would have this joint distribution, and the PICs, it's what couples your random variables beyond independence. Okay, so you may be thinking, how on earth could we possibly compute these from data? Right? How would we do that? In the case where your data distribution is discrete, there's actually a statistical method that seeks to do this. It's called correspondence analysis. Correspondence analysis, you can think about it as the forgotten sibling of principal component analysis in a sense. It's not as popular. But what it does is that it tries to estimate something called a contingency table from data, which is a matrix whose entries are the joint distribution of x and y. You can build that just by looking at count frequency. And if you look at the singular value decomposition of this matrix, if you have a good approximation, the singular of a normalized version of this matrix, the corresponding singular values are your principal inertial components, and the left and right singular vectors are up to a transformation exactly your principal functions. Towards the end of the talk, I'm going to show how you can scale this up for non-discrete random variables using neural networks. Okay, but we'll get there. Cool, so the principal inertial components were not created by me. There is a long history from the mathematical probability, statistics, and information theory literature that study these creatures, dating all the way back in probability in the context of maximizing correlation. Information theorists are really excited about this or they care about this because it's connected to the maximal correlation coefficient and something called strong data processing inequalities. As I mentioned, there are statistical methods for estimating the PICs in the context of the composition of contingency tables, other algorithms such as ACE. And if you want to see an overview of these different interpretations, I refer you to a recent transactions paper by myself and collaborators called Principal Inertial Components and Applications. And what we're bringing to this table is that we apply the PICs to obtain an estimation-theoretic view of privacy, to understand which variables may be proxies for discrimination, and to understand limits of producing good data representations. Okay? So, and each one of the interpretations that we went through, so for example, looking at the PICs as the spectrum of the conditional expectation operator, that will be useful in fairness. The context of decomposing MMSC, we'll use that for privacy and understanding the limits of assuring privacy in data disclosure. And the context of maximizing correlation, that will be useful for representation learning.
Flavio.
Yeah.
Last definition, can you remind us what's the difference with PCA? It looks the same. I'm missing something.
So it's a singular value decomposition of the joint distribution, whereas PCA is the singular value composition of the correlation matrix. So this is, it's not just a scaling. These functions might be highly nonlinear, for example. Any other questions? Okay. So let's go to our first application, which is identifying potential proxies for discrimination. And we're going to be using small perturbations of probability distributions to find which outcomes may contribute to discrimination. And here we're going to be, again, for those who are familiar with the literature in fairness and machine learning, we're going to be looking at one notion of fairness, which is statistical parity. There are many other notions of fairness that are also very relevant. We have generalized this approach to other notions as well, but because of time, I'm only going to focus on one. Okay, so that's just a asterisk for those who are familiar with the literature. Okay, so let's talk about disparate impact. This is the setting that we're considering. Like we have a decision variable x that's used as an input to our model to produce an outcome y. The distribution of x may change when conditioned on a sensitive attribute s. So you have different distributions inducing true potential different distributions at the output of our model. And as a recurring example for this talk, I'm going to use the example of recidivism prediction, mostly because at the end of this part, I'm going to show one numerical example based on a recidivism prediction dataset called the COMPASS dataset. Okay, so this is what we're trying to do. So our goal is to systematically find proxies for discrimination. We assume that your model is a black box. We really don't care about the intricacies of how the machine learning model is implemented, so we just consider it as a black box. And our goal is to do something that looks like this. So assume that you have the set of input features that you use for your model. Just for the sake of example, assume that that's the criminal history, the age, and the charge degree of someone at the moment that they're charged with a crime. If you, just for the sake of illustration, this is not real data, but just as an example, assume that if you look at the slice over a minority population, S equals 0, and a majority population, S equals 1, that has one prior count, age smaller than 25, and charged with a felony, you're going to get that 10% of the population of the minority group and 5% of the majority group fall within this category. If you look at another category, for example, no prior count, no criminal history, age smaller than 25, charged with a misdemeanor, that might be a little bit more balanced between both populations, and so on for other categories. Now we're going to get these features, and we're going to input it to our model, right? And we're going to assume that our model gives a score, in this case for recidivism. And here we're going to assume that the output of the model is a distribution. So you can think about this as a logistic regression or a neural network with a softmax layer on the output or something like that. In this case, if you put in this first combination of features, your model will say, well, 70% chance of recidivism. If you put the second one, no, this person doesn't have prior counts, age is smaller than 25, you might get 20% chance of recidivism, and so on for the other groups. So what we're trying to do is to flag features like these ones. You know, these are features whose distribution is very different between both groups, and at the same time, they receive either very high or very low scores from your classifier, and that indicating that they may be potential proxies for discrimination, right? Because these are features that receive pretty extreme scores, and simultaneously, the distribution is different among both populations. And just to make this concrete in your mind, our goal is that if you give me a black box machine learning model, and you give me a data set that looks like this, I'm going to call this an auditing data set. So it's a data set where you actually have information about the sensitive attribute, the features that you use as an input to your model, and the output of the model. Our goal is to design something that looks like this, a proxy score. You know, so this is just simply going to be some numerical vector that's going to indicate which potential combination of features might be proxies for discrimination. So I'm going to talk about a lot of math, but at the end, this is what we're trying to do. Okay. So in order to accomplish this, we're going to have to understand the geometry of the disparate impact on the probability simplex, on the set of all possible input distributions of your features. And I'm going to define something called correction paths and correction functions that will be useful in building these proxy scores. Okay? So this blue triangle here represents the probability simplex. So what this represents, it's a cartoon that represents the set of all possible distributions over the input features of your model X. Right? So if you ask, what is the distribution over the minority group? That distribution will be a point on this probability simplex, given by this dot here. And when you feed samples from that distribution in your model, that's going to induce an output distribution over the output of the model, given by a point on the probability simplex, on the set of all possible distributions on the output Y. Okay, so we're assuming that we have a disparate impact. So the input distribution over the minority group is different from the distribution over a majority group, S equals 1, inducing different distributions on the output of the model. Okay, and this is just a technicality, but note that there may be several distributions that map to the same output distribution. So several distributions of the input feature that map to the same output distribution, but we're assuming that the distribution over the group P of X given S equals 0 is not contained within that group. So what we're going to do next is a thought experiment. Okay, it's not something that we can actually go and do, but this is just a thought experiment, a hypothetical scenario that will help us build this proxy score. We're going to ask, how should we perturb the distribution over the minority group in order to achieve the same output distribution over the majority group. So if you were allowed to change this distribution, how would you change it in order to equalize the distribution of the outcomes of your model? Right, so we actually have two options here. So the first option is that we follow something that looks like this red path here. We perturb the distribution, continuously change it, in order to perturb along the shortest path that equalizes the output distributions. Another option is to perturb along the green path. So we perturb the input distribution, we continuously change it in such a way that we follow the shortest path that equalizes the input distributions. And since the input distributions will be the same, the output distribution will be the same by the data processing inequality. So what should we perturb? Option 1, perturb along the shortest path that equalizes the output distributions. Option 2, perturb along the shortest path that equalizes the input distributions. Well, since we're just doing math, why not both, right? And what we can do is that we can define a functional given by this complicated expression here, where let me just help you parse this. D is just some distance on the probability simplex, something like KL divergence or some L1 norm between two distributions or something like that. And by varying the values of lambda 1 and lambda 2, we traverse this green path. By varying the values of lambda 3 and lambda 4, we traverse the red path. And of course, we can have a combination of both. And as we change these parameters and minimize according to Q of x, we're going in between the shortest path for both options. Now, why are we doing this? We're doing this because our goal is to build a proxy score. So what we're really interested in is in the beginning of this path. Something like a derivative, like a gradient. We're going to ask, if we were to change the distribution over the minority group by just a little bit, how would we change it? What would be the change that we would do that minimizes this functional here? So which groups would you have the distribution change the most? The outcomes of x would have the distribution change the most. Because the distributions, the outcomes of x that you increase the distribution a lot or decrease the distribution a lot, that the probability a lot, those may be potential proxies for discrimination, right? And in this context, this is equivalent of computing the derivative of this functional over p of x given s equals 0, but it's a constrained derivative because you're restricted to the probability simplex. You're restricted to perturbing along probability distributions. So this is a neat trick. So if you're interested in doing this thing and doing the math behind this, whenever you want to write a perturbation of a probability distribution, one way of doing it is to write this perturbation in a multiplicative form. Okay, so you get your original distribution and you perturb it by 1 plus epsilon f of x. And in this case, the reason you want to do that, because as long as f of x has 0 mean and epsilon is pretty small, this will be a valid distribution. And the corresponding perturbation on the output space will also have this nice multiplicative form given by this expression here, where the function g is simply the conditional expectation of your perturbation f of x given y. Okay, just to make this point clear, if we perturb the input distribution with a multiplicative perturbation, the output distribution is also a multiplicative perturbation. We're interested in something that looks like the gradient, so we're going to make epsilon really, really small anyways. So we can restrict these functions to be in the space of finite variance functions of x. And through the conditional expectation operator, this perturbation is mapped into a point in the space of 0 mean finite variance functions of y. And as we saw in the beginning of the talk, this linear mapping, the geometry of this linear mapping is entirely given by the principal inertial components. Okay, so it gives you, because the principal inertial components are exactly the spectrum of the conditional expectation operator. Okay, so let's do this. Let's compute the derivative in the start of the path. PICs will show up here. In this case, we can formally define a perturbed distribution as your original distribution times 1 plus epsilon f of x. Again, we're interested in a derivative, so we're going to make epsilon really small anyways. So we restrict this function to have 0 mean and unit variance. We're going to have a corresponding a distribution p tilde perturbation on the output. For these perturbed distributions and a fixed f, our goal is to minimize this functional, right, which is this path between these two options of the green and the red paths, of the shortest paths. We're going to be interested in this variation in the beginning of the path, so we're going to make epsilon really, really small for a fixed f. And if we minimize this expression, this functional, over all possible functions with 0 mean and unit variance, you get what we call the correction function. And the correction function is exactly the proxy score that we're trying to build. Okay, so this will give us the perturbation that we're looking for. Okay, so for the rest of this talk, for the rest of this section, I'm going to assume that, just to make this concrete, I'm going to make the distance scale divergence. And we're going to assume that the outcome y is binary, where someone recidivized or not. And in this case, this correction function actually has a very nice form. The form is given here. Maybe you won't find it as nice as I do. But unsurprisingly, the largest principal inertial component, the maximal correlation, shows up here. And the proof follows from the things that are already said, local approximations of KL divergence, and the decomposition of the conditional expectation operator. So look, if you zoned out, and you didn't follow the math that I just said, this is what I want you to pay attention to, because this is what is relevant in practice. So all this math actually represents gives us a very elegant solution for building the proxy function, right? And the recipe for building this proxy score, this proxy function, is the following. You have your model, your predictor, this black box that is predicting your outcome y given x. What this math tells you is that you should design another predictor, just for the sake of building a proxy function that will predict your sensitive attribute s from x, right? So if you give me one estimator for your sensitive attribute from x and one estimator for your outcome y from x, which is given by your machine learning model, I can combine both estimators using this set of equations, and the result f tilde is exactly your proxy score. And of course, this is very intuitive, right? Because if you have features of x that are simultaneously heavily used by your model to predict y, and also are relevant to predict s, those are potential proxies for discrimination, okay, if those values match. So just to give you one concrete example of how you would use this in practice, we're going to look at an example using the COMPASS dataset, which is a recidivism prediction dataset released by ProPublica. In this case, your sensitive attribute, we're going to restrict it to African American or Caucasian. Your set of features is going to be prior count, the gender, charge degree, age, and length of stay. And what we're going to predict is recidivism. And this is an example done on a data set. This is real data collected by ProPublica in one specific county in Florida. And just for the sake of example, we've trained this with different models. We're going to assume that our predictor is logistic regression, and we're going to also use logistic regression to predict your sensitive attribute. And in this case, if you run this on the data set and look at the outcomes that have the distribution change the most, or the least, or reduce the most, you get this collection of features. And I just want to draw your attention to this middle column. So what this indicates is that if you were to equalize the outcome of this predictor trained on the data, the group over the minority group that would have the distribution reduced the most are young African-American males with a large prior count. Right? This is the group that has the largest imbalance between the minority and the majority group, right? And is also heavily used for predicting recidivism because of the number of prior counts. And this also follows what we know of legacies and history of bias in the United States, where young African-American males tend on average to have a higher prior count due to a legacy of policing and discrimination that exists in society. And we can recover this result in the data by using the information-theoretic techniques that I introduced here. We have much more experiments on this, and I refer you to my website, or at the end I'll have some references where you can see more experiments on this data set. So okay, second application, and I'm going to go a bit quicker through this one, is the application in privacy. And the same set of mathematical tools can help us say something very fundamental about privacy, and specifically characterize the best privacy utility trade-off from an information theoretic perspective. And for that, we're going to use the interpretation of the PICs in terms of decomposing MMSE. Okay, and so just that this transition is not too jarring, note that the privacy setup and the fairness setup is somewhat related, right? So in fairness, we had a protected attribute S, your data X, some randomized mapping, for example, a machine learning model that's going to output a decision variable Y. We're going to look at the same scenario, but give different names to our random variables now. So in privacy, S is your private feature. X is data that, for example, your movie ratings that you want to disclose to a data collector. That's going to give you movie recommendations. And instead of disclosing your data directly, we're going to randomize this data through this blue box. And that's what we're going to disclose. And in both cases, both the privacy setup and the fairness setup we would like the output y to be somewhat invariant to changes in this latent underlying variable s, right? So for example, if I change my political preference from Republican to Democrat, you don't want the disclosed movie ratings to change by a lot. Otherwise, someone could be potentially look at the movie ratings and infer the secret information. And so we're going to be looking at this setup for the context of privacy. We're going to make an information-theoretic assumption for the results that I'm going to present now. We're going to assume that this joint distribution is known. Of course, this is not really feasible in practice. We have relaxed this assumption in follow-on work in a paper that we're about to submit to the Transactions on Information Theory. But for now, we're going to assume that this is known just for the sake of the theoretical results that I'm going to give here today. So our goal in privacy is to understand how to engineer this blue box here, right? What are the fundamental limits of perturbation mappings, of how you can distort your data before you disclose it, in order to make sure that an interested party that observes this cannot infer your private feature, but can still provide a certain level of utility. Okay, and we're going to be interested in knowing what are the fundamental trade-offs involved in designing this box. We're considering here a one-shot release model. So we're assuming that we disclose the data. That's what the interested party observes. There's no other interaction here. Of course, real-world settings are much more complicated, but hopefully this will convince you that at least this perspective gives you some insight on how to design models. In this one-shot release model, the problem of engineering this blue box can be formulated as an optimization problem. It will work like this. If you give me a privacy metric, denoted here by F, something that measures some dependence between S and Y, you can think about it mutual information or something like that. And you give me some utility metric, something that depends on X and Y, you can think about that as average distortion. The problem of designing this blue box boils down to solving this optimization problem if the joint distribution is known. One specific, and our goal is to understand the set of achievable pairs, right? What is the set of privacy values and utility values that you can achieve for a fixed distribution between S and X? One concrete instantiation of this problem is when the dependence, the privacy is measured in terms of mutual information, the average number of bits that Y discloses about S, and your utility is measured in terms of expected distortion, right? You want to make sure that whatever you disclose Y is close up to some value delta on average to your original value X. In this case, this problem is convex and can be applied to real-world data sets. A more interesting formulation, at least I find it more interesting, is something called privacy funnel, where here we're measuring both privacy in terms of mutual information between S and Y, the average number of bits that Y carries about S, and while restricting Y to carry at least X bits on average, or sorry, T bits on average about X. So Y carries at least T bits on average about X. This is called the privacy funnel. It was introduced by collaborators of mine, and the privacy funnel is a specific instantiation of a family of sets that maybe some of you have heard of called bottleneck problems. Among them is the information bottleneck. So the question here, you can boil down this question of characterizing the privacy funnel as characterizing the set of achievable pairs between the mutual information between X and Y and S and Y for a fixed distribution between S and X. So for any mapping that I produce, for any data that I disclose Y produced by X, what is the set of achievable pairs of mutual information that you can achieve? So we know that this region will live in this blue, the set of achievable pairs will live in this blue region here because of the data processing inequality. So the mutual information between X and Y is always greater than the mutual information between S and Y. And the truth is that this region will live within this blue convex set here. This convex set, some of you probably already heard of. The upper boundary of this set is what is called the information bottleneck. Has anyone here heard about the information bottleneck? Yeah, some of you, good. And the lower boundary is what we're interested in terms of privacy. It's what's called the privacy funnel. So the information bottleneck is actually, has been studied for quite a while in information theory. There's a beautiful paper, one of my favorite information theory papers by Witzenhausen and Weiner in 1975, where they characterize this region for discrete random variables. It's related to something in information theory called Mrs. Gerber's lemma. We use the same tools as Witzenhausen and Weiner recently in a recent ISIT paper to look at the lower boundary of this region and derive the counterpart of Mrs. Gerber's lemma, Mr. Gerber's lemma, which is relevant to privacy. So we're interested in the lower boundary of this set. But a natural question to ask is, why use mutual information to measure privacy here, right? Mutual information is one specific information metric, but there are potentially many others. And you can, in fact, generalize this problem using something called F divergences, right? Just like you have mutual information that measures the dependence between two random variables x and y, for any other set of divergence measures, you can define a similar quantity, which is named F information. And the reason you would want to do that, because there are many F divergence measures that you encounter in the, for example, statistics and machine learning literature, things like total variation, chi-square, Hellinger distance, and so on, that might carry some statistical and operational meaning. And specifically, we're going to be interested in chi-square divergence. So chi-square divergence, if you're familiar with mutual information, is just like mutual information, but without the log here. And the reason we care about chi-square divergence is because chi-square divergence is directly related to the principal inertial components. So the sum of all the PICs is exactly the chi-square between x and y. And recall that the PICs say something about how well you can estimate functions of x given an observation of y. Okay, so just to make this more concrete, if we do a PIC decomposition of two random variables, x and y, we end up with two things. First, we end up with a set of basis functions of x, right? So that comes from the decomposition, a set of uncorrelated orthogonal functions of your hidden variable x. And for each one of these functions, we have a corresponding singular value, which indicates how well you can reconstruct that function in a mean squared error sense, given an observation of y. Why is this neat? Because, well, if you give me a basis of the space of finite variance functions of x, it's a basis, right? So any function that also has finite variance of x can be written as a linear combination of this basis. Note that this is a linear combination, but these functions might not be linear themselves. So it's a linear combination of nonlinear functions. And this basis is very convenient, right? Because you can decompose the MMSE of estimating this function x from y in terms of this basis. So it's going to be the square of each one of these coefficients times 1 minus lambda I. OK, so now recall that chi-square captures the sum of all these guys here, all the principal inertial components. That means if that chi-square is really, really small, all the PICs are small, and specifically there is no function of x that can be reliably reconstructed from y. So you get something that's akin to privacy. On the other hand, if the chi-square is very, very large, there may exist functions of x that you can reliably reconstruct given an observation of y. So that's something that's akin to utility. So we have many results on this. I'm going to show one result next, which characterizes the set of achievable pairs of chi-square between x and y and s and y. So that's somewhat related to the information bottleneck. So we call here the estimation bottleneck. Okay, so we want to look at the set of achievable values of chi-square between x and y and s and y for a fixed distribution between s and x across all mappings between x and y. And the reason we're looking at this, because in about 5 slides, you're going to discover that analyzing this region actually says something very fundamental about the limits of perfect privacy. So that's where we're going with this. Okay. So in this case, chi-square also satisfies the data processing inequality. So the set of all achievable pairs lives in this blue region here. And I'm going to prove one result on that, which is a sharp lower bound for what we call the estimation funnel for the privacy region here. So check this out. So remember that if you give me the joint distribution of s and x, I can do the PIC decomposition of that joint distribution. What I end up is with an orthogonal basis of the space of finite variance functions of s, f1, f2, fd minus 1, all the way to fd. And through conditional expectation, right, you're going to map that to a basis, a set of orthogonal functions and correlated functions of x. Okay, so and where g1 is the MMSE estimator of f1, and you can think about f1 here as being the function that's the easiest to reconstruct in this mean square error sense, the one that you could, in theory, reconstruct with the smallest error, and fd being the one that is the hardest to reconstruct from s given an observation of x. So our goal is to design this blue box here, right? What we want to design is a privacy mapping. So we're going to randomize x, somehow randomize your movie ratings, delete some movie ratings in order to disclose some information. And in this case, if you're only allowed to disclose a little bit of information about x through y, right? you would probably disclose in the direction of the function that corresponds to the one that's the hardest to estimate of about S given an estimation of X. Hardest, I mean the one that can be least reliably reconstructed in this mean squared error sense. So you would design this randomized mapping so that given an observation of Y, the only function of X that you could potentially reconstruct is g of D, the one that's aligned with the function that's the hardest to estimate about S given X. Of course, we don't know if we can actually design such a mapping. That's why it's a lower bound, and it gives us the very first part of this region. Now, if I allow you to disclose a little bit more information about X through Y, probably would disclose in a direction that's aligned with the second hardest function to estimate from S given X. Right? That's the function that you would like to be able, you would allow to be reconstructed from X given an observation of Y, because given that function, you can't really reconstruct, well, any function of S except these two. That gives us the second piece of this lower bound. And if you proceed like this, you get a lower boundary for this region. Now, what I like about this region is the very first step, right? This very first step tells you tells you something fundamental about the limit of perfect privacy, right? Because what this says is that if the smallest principal inertial component is 0, what that means is that you can disclose some information about X through Y while keeping perfect independence from S. And you can show that that's a necessary and sufficient condition for perfect privacy, that you can only achieve perfect privacy, reveal some information about X while disclosing nothing about S when the smallest PIC is 0. And that means that you can walk on this plateau here. You know, you can disclose some information while keeping this information 0. And you can reverse this argument and derive an upper bound for what we call the estimation bottleneck that also tells you which functions, how would you compress X in order to assure that at least some functions of S can also be reliably inferred. You can find much more results and applications to datasets in a recent preprint that we have on arXiv that was done by 2 students here at Harvard. So, okay, that's what I was going to say about privacy. And now for the last part, I'm going to quickly go over some results in representation learning and show how the PICs can also be used to reason about complicated representations learned by complex machine learning models, specifically by looking at it in the context of maximizing correlation. And this will allow us to scale up one specific statistical method called correspondence analysis by using neural networks. So how could we estimate the PICs, right? I mentioned that a little bit earlier, that if your data is discrete and over a finite alphabet, one way of estimating the principal inertial components is by estimating this matrix here, and by looking at frequencies of counts in your data set. And this is, in fact, what one specific statistical method called correspondence analysis tries to do. Now, this method is somewhat limited. First, because it requires your data to be categorical, right? Both X and Y has to be distributed over a discrete data set. And also, it doesn't really scale up for high-dimensional data, right? Because if the alphabet of your data is really, really large, these are really large matrices, and they're hard to estimate with limited samples. And other methods for estimating the PICs also run into similar problems. So in order to try to circumvent the need of estimating this matrix directly, one thing we have to do is go back to the drawing board and look at the PICs as the solution to this optimization problem in the context of maximizing correlation. Note that we would not need to estimate this directly if we could solve this optimization problem where we're maximizing the correlation between X and Y subject to functions having 0 mean and unit variance. But of course, solving this optimization problem at first glance doesn't seem feasible, right? Because it requires us to search over the space of all real functions of 0 mean and unit variance of X and Y. But luckily, over the past 10 to 15 years, we've been developing very, very, very efficient ways of searching over very large space of functions by indexing them through neural networks, right? When I think about a neural network, I think about the output of each neuron as a point, right? So each neuron gives you a point in the space of finite variance functions of the input distribution of the samples of your network, right? So f1 of x is simply a point in the space, f2 of x is another point, but of course, this is a space of functions. So and you can assume that these functions have bounded variance, right? So if we restrict our search over functions of x indexed by neural networks, representable by neural networks, and functions of y also representable by neural networks, as long as we can design a loss function that represents this maximal correlation and backpropagate over this loss function, we could potentially do correspondence analysis at scale, right? And luckily, we can design this loss function. This loss function is given here. Where CF and CFG are simply correlation matrices between X and Y. These are things that you can estimate over a batch. You can remarkably implement this in TensorFlow and backpropagate over it, and actually fit neural networks to find these maximally correlated representations. I'm not going to go over the details, but it's related to something called DCCA, and you can find deep canonical correlation analysis, and you can find details in a recent archive preprint. So let's see how this works in practice. So the first case, let's validate this architecture using synthetic data, right? Remember, one of the limitations of building that big matrix of counts and doing the singular value decomposition of that, because it wouldn't really extend to continuous random variables. So let's try to extract these principal inertial components and principal functions using neural networks when X and Y are continuous, and specifically when they're jointly Gaussian. In this case, the principal functions are neighborhood friends, the Hermite polynomials, and they're given by this expression here. And you can actually produce samples from jointly Gaussian variables and train this neural network, backpropagate on this loss function, and you can actually see that it reconstructs fairly well the Hermite polynomials from data. Okay, we've validated this with also some other synthetic data sets. So the neat thing about this is that now when you apply it to real-world data sets, is that you can use correspondence analysis at scale. And it would work something like this. You would have, if you have samples from X and Y jointly distributed from a IID sampled from a joint distribution P of XY, you can fit the principal functions of X and Y using neural networks. And you can do something called a correspondence analysis factor plot that captures nonlinear relationships between these variables, right? So one way of doing this is that if you fit these neural networks, you can plot, for example, f1 of x and f2 of x, the output of these first two maximally correlated functions for all the samples in your data set, and put in the same plot of samples from y, also of g1 and g2 of y. And based on this analysis, try to extract correspondence, right? Try to extract common nonlinear factors between your data points. So let me give you one example on how to use this in real-world data sets. When X, for example, this is produced from data by the Kaggle food competition sponsored by Yumly. You can download this data from Kaggle. This is something about a few, like tens of thousands of recipes. So X that we're going to input here are recipes. So it's a vector of ingredients where 1 if that ingredient is present in a recipe or 0 if not, and Y is the cuisine. And you can go and train neural networks to find these maximally correlated representations and plot them in this bidimensional plot. This is something you could not do before if you were to use standard correspondence analysis. And you can see that it extracts correspondences between your data. For example, the Asian cuisines are all in this corner. You have Japanese, Korean, Chinese. You have Filipino in between Indian and Chinese. In the upper right-hand side, or I guess left-hand side corner here, you have all the European cuisines. You get some interesting correlations. For example, Cajun is close to Spanish and French. You also see southeastern US and Moroccan close to this influence. This method sometimes tends to overfit, so you see Mexican here in the bottom. Each little green point here is one possible recipe. You can also see how the ingredients position themselves in this plot. And you can actually see, for example, here sesame, fish, and soy is closer to the Asian dishes. Salsa is closer to the Mexican, and so on. Brazilian is right in the middle, so I know what that means, but that's also just the first two principal inertial components that are plotted. Another experiment that we did on this was just recently accepted. We're going to present this at a NIPS workshop on ML for a developing world. This is another example that we did for data from Brazilian Congress. So Brazil has a remarkably good open data program for government expenditures. And you can actually go and access all the discretionary expenses from Brazilian congressmen dating all the way back to 2009. It's about 3 million sample points. Here we use X Congress member and the party that they're part of, Y the expense category and the value. And you can also do these correspondence analysis plots. It's a little bit hard to interpret here really quickly, but you can see that there are certain expenditure patterns, for example, disclosure and advertisement of parliamentary activity, that you clearly see a deviation in behavior. And this is consistent with what you observe with the data, that this is a category that seems to be used for, which seems to be misused. So, and we've also scaled this up with other data sets. This is just one example on Cypher 10. We've done it for Cypher 100. In this case, it's harder to interpret because you're interpreting pixels and labels. But this is just to illustrate that you can scale this up for very large data sets. And you can find more results in our recent arXiv preprint. OK, I already ran out of time, so I'm just going to very quickly go over some of the ongoing work that we're doing in my group. I'm always looking for people to work with. So if you find any of this interesting, please do come talk with me. I would love to chat with you. And this is some of the stuff that we're doing. So detecting and measuring and assuring fairness is a very complex problem. The results that we presented are fairly limited in the sense that, for example, there may exist other unobserved confounding variables that might causally explain the discrimination that you observe in your model. It's interesting to ask, how could you potentially incorporate this in this framework? There is, for the math aficionados in the room, and statistics aficionados, there seems to be a connection between the local perturbation approach that we presented here and things from robust statistics and influence functions. So if you're interested in exploring that more, this is something that we're ironing out. We've generalized this approach for many other fairness metrics, things like equalized opportunities, error rate imbalance, and so on. You can see this in a recent preprint. It should be on arXiv in next week, probably. Another problem I'm really curious about is quantifying the impact of data set size and diversity in machine learning algorithms. For example, if you go and search and you Google wedding and look at Google image search, you're going to get a lot of brides in white and grooms in a suit. That does not necessarily match our diverse notion of what a wedding is. Right? So a natural question to ask is, theoretically, how diverse should a data set be in order to assure that applications and machine learning models trained on that data set also produce diverse and fair outputs. Another area that we work on is also on learning fair data representations. So how would you produce a new representation of your data so that machine learning models trained on that representations are fair? If you're looking for more resources on understanding fairness in machine learning, I recommend this recent IBM toolbox called AI Fairness 360. They have a lot of these preprocessing algorithms implemented. This first preprocessing algorithm is actually my algorithm. They will give a talk here. Awesome, yeah. So this first algorithm is developed by me while I was at IBM. And I think they have a really cool stuff implemented there. And there's a good resources just for you to look at different implementations and definitions. OK, so to wrap up, I already ran out of time. With big data comes big responsibility. And information theory and theory in general can help. Okay, so I do believe that information theory and math in general, but specifically information theory, can help us understand the fundamental limits of systems that process data and also help us understand how to make them fair and private and transparent. This is just a recent few papers that were produced by my group in Privacy and Fairness. The code that we use here is all available on GitHub. Specifically, the results in the fairness section is available on this GitHub repository. And yeah, thank you so much for your attention, and we'd be happy to take questions.
Given that we have a little bit more time, maybe we have one or two questions.
Yeah, sure.
People can come and ask this other
Go ahead.
Is it possible to turn this the other way around? Just trying to reduce the information to increase it for experimental design. Would this work?
It might work, yeah. So I think that's the focus of the information bottleneck. Yeah. I think especially over the upper part. Yeah, it's the upper part. Yeah. I think, yeah, it might work. There are some recent results that try to do exactly that. Yeah. So this is kind of the negative part of it. The positive part would be to, boost it.
Have you seen any experimental work for advertising data sets by releasing some reduced representation?
I'm sure, I personally can't cite one off the top of my head. But yeah, that would be a very interesting application area for that.
All right, since we're over time, I think we thought that people can come and talk to you.
Okay, sure.
There was another question.
Yeah, I think Joy had a question. Yeah.
So you said some of your future work is focused on transparency transparency within data sets, particularly image data sets, with the example that you showed with the wedding. Can you share a little bit about what your group is exploring in that domain?
Sure. I think for now we're still mostly in the theoretical domain. Like we're asking questions of how many samples do you need to discover discrimination, right? And for example, especially if you're building data sets where you're mixing samples from different populations, how does the imbalance of that mixture, I think it's related to some results, like how does that imbalance of the mixture potentially impact the performance, but trying to bound that impact from a theoretical perspective. I think I would love to chat more about potential, more practical aspects of that. But for now, it's mostly on trying to derive generalization bounds based on this imbalance in the mixture of the distribution. Yeah.
All right, thank you.
Thanks.